I see the red line. Okay, cool. So it's recording right now?
Yeah.
Okay. Oh, so welcome everyone. Today we have Dr. Hong Yu. Dr. Hong is now an NCAR ASP postdoc fellow at HAO, hosted by Dr. Kevin Fine, Wenbin Wang, and Gang Lu. He received his PhD in space physics from University of Texas, Arlington in August 2025, where he was advised by Dr. Deng Yue. His research focused on understanding inter-hemispheric asymmetries in the thermosphere and ionosphere and their impact on geospace through a combination of observational data and numerical models, including space weather modeling framework, SWMF, and global ionosphere-thermosphere model, GITM. Now at HAO, Dr. Hong will investigate mass transfer between thermosphere and ionosphere and the magnetosphere use coupled TIGCM and Hydra semi-3 simulation. So let's welcome Dr. Hong, and he's going to present the inter-hemisphere asymmetric and its impact on the coupled magnetosphere, ionosphere, and thermosphere. Yep.
Thanks, Jiting, for the introduction, and really appreciate everybody spending time to join me today, in person and remotely. So this presentation is mainly based on my PhD thesis, which I defend in this August, and I want to thank all my co-authors through the collaboration of NASA GDC mission and NASA CUSE mission for helping me with this project. And I'll be talking about everything related to inter-hemisphere symmetry. So first on the high-latitude region, and then the impacts on the whole MIT. Quick outline. So I know everybody here from very diverse background, all the way from solar to the lower atmosphere. So I'm gonna introduce some fundamental conceptions which are involved in this study and open questions. And then I'm gonna go over three main results which I used to answer the question raised above. And finally, the summary and future work. So let's start with the magnetosphere, and we know it's a very complicated system. And we just want to simply split up into two parts. And first one is the inner magnetosphere, which is inside the black circle, and it's mainly dipole field and controlled by the Earth's rotation. And the part is the ring current, which intensifies during geomagnetic storm. We're going to cover a little bit of the ring current. And then very simple, the outer magnetosphere, which is highly controlled by the interaction with the solar wind. And so you can see the solar wind is coming in from the left. And we're gonna cover some structures such as the night side magnetic tail and also the day side magnetic path in part of my study. And you probably noticed that there's very tiny pink layer here. That is the ionosphere-thermosphere. And basically they are overlap regions, and we know they are the upper part of the atmosphere. And the atmosphere gonna absorb the heating from the solar. So as you can see, the attitudinal profile on the left of the figure is very high temperature. So that's the reason why this is called thermosphere. And the main species is just neutral particles. And on the other hand, we have ionosphere, because the solar flags not only heat the atmosphere, but also ionize it. That's the reason why we have ionosphere. There are charged particles, and basically the ionosphere, thermosphere, the overlap regions. And it's based on which particle you care about, like neutral particle from thermosphere and charged particle from ionosphere, but they are coupled. And then a little bit high-latitude electrodynamics. Obviously, this is happening in the high-latitude region, and we have the diagram showing here. And firstly, we have the orange sheet. That is the field current, and you can see the very dynamics moving from MPIC field current observation. And we have the purple one, that is the electromagnetic field, and which can form the two zero convection in the ionosphere height, and typically one positive in the downside and negative in the dusk side. And that is the convection patterns. And also we have the green one is particle precipitation. So that's the reason why we have a very bright and organized aurora zone, and typically in the night side, and that's the particle precipitation. And also we have heating in the ionosphere. We more care about the Joule heating in the ionosphere. So this is transfer energy from magnetosphere to the ionosphere height. And these are quantities we covered. And then open question. So why do we study inter-hemisphere asymmetry? So why do we care about the two hemispheres, they're same or not? And this is a very critical science issue, and our geospace community has insufficient understanding of the nature of inter-hemisphere symmetry. So for example, we have DMSB observation. And in this study, I'm going to use NH for Northern Hemisphere and SH for Southern Hemisphere, because we're going to do a lot of comparison between two hemispheres. And you can see basically their satellite trajectories. They have very different data coverage between two hemispheres. So it's very hard to study inter-hemisphere symmetry. And super long, we always have more data from the Northern Hemisphere. So that means asymmetry study, they requires extensive simultaneous observation from the two hemispheres, but it's very challenging to observation study. And on the other hand, we have simulation. So this is a widely used potential model, which is Weimer. And you can see at this specific time, Northern Hemisphere on the left and Southern Hemisphere on the right, they're almost identical, which means most of our models, they are developed assuming inter-hemisphere symmetry. So if we want to study asymmetry, so we need to modify the models. And this is the open questions. And then we have question number 1. So we want to understand why and how the two hemispheres, in terms of ionosphere-thermosphere, were in short IT, they are asymmetric. And very simple, on the top left, we have the auroral precipitation, this one observation. And again, northern on the left and southern on the right. And you can see the magnetosphere forcing like the precipitation, they are asymmetric already, because these are drivers to the IT system. And then we have the, let's look at IT. So the bottom figure is GPS TEC observation, and basically the electron density. So we don't really understand why the bottom part, which southern hemisphere, they enhance much earlier. There was some time delay in the northern hemisphere. And also for neutral density on the top right, and you can see during this specific time, I believe it's a geomagnetic storm. And they have enhanced neutral density, but we don't really understand why this. So the northern hemisphere is always like much enhanced compared to the southern hemisphere. So everything here, they're evolving the inter-hemisphere symmetry, which need further understanding. And also I want to emphasize the symmetries, they can be different forms. They can be different magnitude, they can be different distribution, they can even be different like time variation or time delays. And so to answer this question, we're going to have result 1. We're going to study drivers and effects of the ionosphere-thermosphere inter-hemisphere symmetry. So before I dive into the details, I want to mention, so this presentation is mainly like a result. And if you're really interested in the methodology and this stuff, and I have that one in the backup slides. And so here we go. The model we are using throughout this study is the GITM, Global Ionosphere-Thermosphere models. It's very similar to TIATCM, as everybody know here. And then, as I mentioned, we need the high-latitude driver to drive GITM. So, because this is a mechanism study, and empirical model should be enough. And we typically use polar cap potential from Weimer on the left, and we use precipitation from HLA. Both of them are empirical model. And then, based on our investigation, we found 4 main drivers, which can lead to symmetry in the IT system. So everything here is showing electron density at E region, because this is related to the dipole effect and also Joule heating at E region. And we found the 4 mechanisms, which are 4 columns. And the first one is seasonal variation. Second one is geographic configuration. And third and fourth one is from the magnetosphere, which is the precipitation and MFBY. And all the top row, they're from the northern hemisphere. You can see NH, and middle one is southern hemisphere, and bottom one is the difference between the two hemispheres. So which is the so-called inter-hemisphere asymmetry. If you see something in the bottom, that means the two hemispheres, they're asymmetric. And I want to briefly mention the second column, which is due to the real geomagnetic field configuration. And last week, Kapesh had a really nice presentation talking about the UT variation going to change the MI coupling, which has some feedback on the magnetosphere. This is because you can see at any time the two hemispheres going to have different distribution of the auroral zone. which is the yellow circle. And like for this time, the northern hemisphere is more close to the day side, and the southern hemisphere is more close to the night side. So you're gonna change the local time dependence. And if you like some values, and this table just summarize all the symmetry index as we define in this equation, and how these are related to the four mechanisms. So firstly, the red one is due to solar radiation symmetry. They're going to cause symmetry for all the four quantities. And typically, you can see the first column, electron density at E region, and the symmetry can be up to 90%, which is a very big value. That means seasonal variation leads to a dominate in general conditions. And second one, the blue color is related to the B field configuration, and they're going to lead to symmetry, but most importantly, they're going to introduce the UT time, like a shift of the IT quantities. And third one is the symmetry precipitation. So if the two hemispheres have different precipitation input, and they're going to lead to some symmetry. And finally, MFBY, they're going to change the asymmetric pattern distribution of the convection, which leads to some symmetry in like neutral density, neutral wave patterns through the I-neutral coupling. And so we want to rethink about this. So have we really solved the problem? Because I want to have you attention at the very top row. So this one is in black color. So for this round, we just keep the four mechanism to be identical between the two hemispheres, and then we double check the symmetry. As you can see, the symmetry value is very small. So that means if these four mechanisms, they are symmetric between two hemispheres, and then the IT quantity, at least this quantity should be almost the same. And something we probably didn't cover in this study is something from lower atmosphere, because I know some people study lower atmosphere like tides, waves, they also have some contribution. But since we focus on the high altitude region, especially during storm, they're going to be dominated by the magnetosphere source instead of the lower part. But lower part is could be very important in middle and low latitude region. And coming to the conclusion, we found four drivers. From internal, that is the geographic configuration. From external, we have seasonal variation, precipitation, and BY. And also we noticed season gonna dominate the symmetries, and B field gonna lead to the daily variation. And the other two forcing, they can be enhanced during geomagnetic storm. So let's talk about geomagnetic storm. And we're gonna study the rain events. And again, we use Gator model, but for rain events, we decide to use the high-latitude driver based on real observation. The first one, we use a film current from MPIC. And again, let me play the movie so you can see it's very dynamic. And we're gonna use AMA pattern, that is data simulation model, which based on real observation and as the precipitation model. And then we're gonna use the NCAR three-dimensional ionosphere electrodynamics solver to get the global potential. So basically, this is solved by the current continuity equation and also the Ohm's law equation. You have the film current on the right-hand side that's passing from magnetosphere to the ionosphere. You have conductance, which is sigma from precipitation, and also from the day side solar flux. And you have neutral wind U from Gator simulation, and then you can get the electric field E, and do the gradient that is potential phi. So it sounds very simple, but actually it's a very complicated system. So this is the version of the neutral dynamo used by Astrid and also coupled to Gator by Qingyu Zhu. So I don't want you lost in the equation, but basically what we're doing here is two steps. So the first step, we're gonna get the high altitude potential in the two polar regions between the two hemispheres. And for this step, we're gonna need to think about which region field current to take in. So we're gonna set a boundary at 40 degrees, and above that, we're gonna use the field current from magnetosphere, and below that, we're gonna remove. And the second step is after we get the potential in the high latitude region, then we're gonna get the global potential based on the high latitude potential, and also in the boundary behind the boundary, that is a closed field line. We're gonna do everything just the same between two hemispheres because it's equal potential. And still, we need to set up the boundary, and here we choose 55 degree, and above that, we're gonna use the potential from magnetosphere, and below that we use the potential driven by neutral wind. And then between them, we set up a transition zone. We're gonna use both neutral wind and contribution from, and also use the magnetosphere contribution, but based on some terms. And basically, And so this is the dynamo we're using, and we are definitely looking forward to the new dynamo, which I developed here at NCAR, and we can look forward to that. And so very quickly, we choose the storm event is October 2012. So probably you can guess why we choose this storm. If you can see the shaded region, and we have very stable BZ, and that means the energy and everything dynamics gonna go into the magnetosphere. And we have the By very stable to keep a positive value and quickly reverse to a negative value. And hopefully you still remember the full one of the mechanism for symmetry is under By. So for this event, we can take a look at the By effect typically during this time period.
Is IMF-BX important?
That's a really good question. I remember in 2022, you asked the same question. I did check, there were some paper to study because By going to change the reconnection efficiency between the dusk downside for the two hemispheres. And Bx also changed. Like if Bx is positive, and they're going to change, the northern hemisphere is going to have like a much quick reconnection compared to the southern hemisphere. But in general, like they're both important, but By seems like more important because it's more efficient to change the high-latitude forcing. Yeah. So and we take a look at two quantities. So the top row is cross-polar cap potential, CPCP, and bottom one is hemisphere power, which basically is the hemisphere integration of the particle precipitation, the energy. And we still have the first column. This is from round one, we call it empirical model as a reference. And the second column is run two, which is driven by realistic drivers. We use the AMI pattern for precipitation. We use ambient field current to get potential. So you can see run two on the right part, and they have more temporalization, and also they can better showing the symmetry, right? The two lines, the orange one is from northern hemisphere, and blue one is from southern hemisphere. And you can see they have more symmetry, also have the By response. Looks like compared to the right one, the right one CPCP almost identical, but which could be not reasonable. And that means if we want to study in-hemisphere for real storm, we need to use realistic drivers. And a little bit about the By effect, and as I mentioned, By going to change the reconnection efficiency between two hemispheres. And so this is our simulation results on the middle. And we pick this time is By is positive. You can see from the top is positive By. And positive By for the northern hemisphere means By is pointing from dawn to dusk. So you can see the dusk side on the right, the northern hemisphere is much lower latitude extension and also have a much larger correction pattern compared to the red one, which is the downside. And this is opposite direction for the southern hemisphere. And so, for example, like if you check the downside, the northern hemisphere is much higher latitudes, and I think almost 70, 75. But for the southern hemisphere, is roughly like 45, 50. So that means not only the IMF-By changing the convection, the pattern, but they also change the extension of the convection patterns, which gonna have some feedbacks affection on the middle and low latitude region. And because we are doing simulation for real events, and I want to mention that we did model comparison for all the studies. Like for this one, we compared the two simulation from GATEM with the DMSP observation, and generally speaking, the simulation can reproduce the high-latitude ion convection really well. So that's the reason why we did this kind of study. And coming to the conclusion is real storm require realistic drivers. Otherwise, we don't see like a reasonable symmetry in the results. And also, both the high-latitude convection and its equatorial extension have a strong By dependence. And let's do just one more step. Because now we know we have field current, we have precipitation. So we wonder which one can lead to more symmetry in the IT system, or it leads to symmetry in the high-latitude dynamics. So this one, we're showing the two lines, and the methodology is a little bit complicated, but basically the difference between the two lines is due to asymmetric precipitation. And you can't see too much difference between the two lines, but we have the same thing, but on the bottom, that is due to asymmetric field current. And now the difference is very obvious. That means in terms of causing asymmetry to the high-latitude forcing and further in the IT quantities, asymmetric field current leads to more contribution compared to symmetric precipitation. And also, it's not hard to imagine. Symmetry can be asymmetric magnitude and can be symmetric distribution. So now we wonder, is the asymmetric magnitude or asymmetric distribution? So which one give more contribution? And again, we have polar cap potential on the top, and we have geoheating on the bottom. This is the highly integrated geoheating. And we have the first column, this is due to asymmetric magnitude. And the second column is due to asymmetric distribution. And it's not hard to imagine. So if the forcing distribution is asymmetric, they're gonna lead to more contribution to the symmetry in the dynamics, and they're gonna further change the IT quality. And this reminds me of some previous study, because previously when we quantify the symmetry in the IT quantity, we just use the definition like this. But this is mainly based on magnitudes, like total phelan current or CPCP. These are like magnitude values, but it's not included any distribution information. So, which could be not accurate. And then we define a new symmetry index, which is like this. This one gonna cover the 2D distribution, because it's not hard to imagine if the two hemispheres have the same energy input, but the energy distribution is very different. We can still see a lot of symmetry. And that means we do need the 2D information to quantify the symmetry. And come to the conclusion in terms of causing symmetry in the IT system and high-latitude forcing, phelan current has more contribution compared to precipitation, and asymmetric forcing distribution has more contribution compared to asymmetric forcing magnitude. And also we define a new symmetry index, which better quantify the symmetry in the IT. And so far in this study, we have been talking about the symmetry in the IT system. But now we're gonna look at how the symmetry in the IT system feedback to the magnetosphere. So look at this really cool movie. And we're gonna study a total solar eclipse, which happened in December 2021. It's the northern winter and southern summer. And suppose the southern hemisphere had much larger flux and solar flux and more conductance compared to the northern. But we have the solar eclipse happening in the Antarctic region, and they're gonna dramatically change in conductance. Through the MI coupling process, they should have some feedback on the magnetosphere, the whole geospace. And then let's check it out. So we're gonna study the impact of IT symmetry on the magnetosphere. So again, we use GATEM for the global ionosphere-thermosphere simulation. And so based on the solar observation, we're going to get something called radiation mask. Just think about the shadow chaining due to the moon. That is the mask. We're going to cover the conductance, cover the region. We're going to see some chaining in the conductance. So after simulation, we're going to get the ionospheric conductance, and then we're going to use this one to drive SWMF. So basically, we use 3 different components of SWMF, and the top one is Vector Rush MHD model is similar to Gamera for MHD domain, and we have RCM for in the magnetosphere, the ring current study, and also similar. And also we have RIM model, RRM. This is the 2-dimensional Poisson solver for the ionosphere electrodynamics, which I think is similar to RIMX. And you can see we're going to take the conductance from GATEM, from the ionosphere-thermosphere part domain, and we're going to get the phelan current all the way from magnetosphere passing to the ionosphere height. And use the Poisson solver, we're going to get the electric potential, or we can get electric field. And then we're going to feedback electric field back to the magnetosphere and back to the inner magnetosphere. So this is how we study the feedback of magnetosphere to the solar eclipse. And very simple methodology. And so first, let's take a look at the ionosphere response to the solar eclipse. And we have 2 rows, and the top one is Peterson conductance, and bottom one is Hart conductance. And first column is the without eclipse, and middle one is with eclipse. And we have the very right column, that is the difference between the 2 rows. So that means if you see something in the third column, that is the conductance response to due to the solar eclipse. Let me play the movie, and you can see, okay, we have some red values, and this is the conductance change due to solar eclipse. And now I want to have your attention again, because you probably noticed there were some contour lines. So the contour lines, that is the solar shadow, which is due to the moon, and you can see how the shadow changing with the conductance. Now let me play this one again. And if you focus on the third column, you can see the red value is going to change with the shadow which very consistent with the study. And that means basically gallium simulated ionosphere conductance has always responded to the solar eclipse effect. That means we can study use this conductance drive SWMF to see some response in the magnetosphere. And now directly the magnetosphere. So top row is plasma pressure, and bottom one is plasma flow. We have everything plotting the x, z coordinates, and that means we're gonna look the Earth from the side. And so let me play this one, and you can see the two columns is without eclipse and with eclipse. It looks almost identical, but after some time, I think, because the eclipse peak time is 7:30 right now, and then you're gonna see some difference between the left and right animation. Like now, you can see some difference. So the reason why we have this changing is because through the MI coupling, think about the equation I was showing. You change the conductance, there should be a change in convection patterns, which is the CPCP. And CPCP is related to the open magnetic field configuration, and you're gonna have the flow changes. So that's the reason why you see the tail region, the ion flow is changing. And which means the effect of solar eclipse on global magnetosphere is significant. And if you want to do some mathematics study, and then we try to trigger the points, on the top you can see there were some magnetic field lines. The red one is called the last close magnetic field line. So we're going to trigger the point on the x-axis, and we plot the linear figure on the bottom right. And you can see that for the two cases with or without eclipse, and before the eclipse, the two lines looks almost the same. But due to the solar eclipse and the location changing of the magnetic tail is different, and the maximum difference could be up to 16 Earth radii. So this is like a mechanism study. We're gonna see some response in the magnetosphere, but for the values, I think we need further investigation, like comparing with some magnetosphere satellite, and which we have been doing right now. And definitely we shouldn't stop here, because previously we studied mechanism, the solar eclipse effect on the IT system. We just do simulation like this. This is driven by empirical model, which only include the solar eclipse UV effect. But now we have some feedback from magnetosphere, so they should have some further effect on the IT again. And we're gonna take the horizontal neutral wind at F region as the example. And so top row is driven by it's only solar UV effects, and bottom one is solar UV effect plus the feedback from magnetosphere. So which originally from solar UV effect, but it's from magnetosphere directly. Because typically we do the solar eclipse study, we're gonna do the top simulation, but now we have bottom one, and you can see at some specific time, like the left column, and it's 7 UT and before the eclipse, and they look almost identical. But after that is 9:30 UT, you can see they are very different, because the bottom one, they include some feedback from magnetosphere. So coming to the conclusion, that means the eclipse effect from magnetosphere to the IT system is not negligible. So we do need to include them. And I think the main takeaway is very similar to the study, and we study the ionosphere response, which is the TC and conductance drop due to solar eclipse. And then we look at the magnetosphere response. We have the changing of both the day side magnetic poles and the night side magnetic tail, and also the location change up to 16 Earth radii. And finally, we look at the magnetosphere feedback to the IT again. And there are some significant changing due to magnetosphere in the neutral wind. And then quickly, we look at another event, which is the superstar. We want to study the GMD, geomagnetic disturbance, because typically when people study GMD, like showing the figure we have from downloading, and people mainly care about the contribution from magnetosphere, like from ring current, from field current, something like that. But what are we thinking is how an ionosphere thermosphere model can do. Because ionosphere given the three-dimensional ionosphere currents without any assumptions, and with some the development, we can get the neutral wind driven current on GMDs. So they're gonna further have some feedback to the magnetosphere. So let's check it out. And this flow chart just to introduce the methodology we used in this part. And the top one is the magnetosphere domain. We're going to use the SWMF simulation. And bottom one in the green color is the ionosphere-thermosphere domain. We're going to use GATEM again. And so as I mentioned, we have the neutral wind current. And then first we want to look at this neutral wind current, their contribution to GMDs by adding this loop. And secondly, the neutral wind should have some feedback to the magnetosphere. So we're gonna check very simple, like first step, by looking at the neutral wind current on magnetosphere. And first, let's just pick one specific station, which is the BOU, which is Boulder. And we have we're plotting the north component of geomagnetic disturbance where WN as a time variation. So during the mid-2024 superstorm. And first, I want to have your attention at the green line. So the green line is directly from GATEM simulation. And also the black line is from SuperMag observation. So you can tell from the two lines, the green and black, and they look very similar variation, but in terms of magnitude, they look like a shift between them. So my explanation is GATEM, there were no ring current effect in GATEM and the GCMs. So SWMF can simulate the ring current effect. The ring current is showing on the bottom, which is the blue line. So if we back to the top panel, now we have the blue line again. The blue line is now GATEM plus ring current. So you can see with the ring current effect, the GATEM simulation is much more better compared to real observation. And something we want to study is also the neutral wind contribution. And if we back to the bottom figure, we have the red line that is U cross V, which is the current, which is the GMD due to neutral winds. And you can see during storm main phase, as indicated by the words main phase, the neutral wind contribution is much smaller compared to the blue one, which is the ring current. But after that, typically the recovery phase, you can see the red line is much larger, the magnitude compared to the blue line, which is the ring current. Because during the recovery phase, the magnetosphere forcing gonna shrink back to the polar region. And at that location, so the relative contribution from neutral wind gonna be important. That's the reason why the recovery phase has more contribution. And I think most of you guys last year, you remember the May 2024 storm. You can even see the aurora at Boulder. So that means we can't directly use the location to define, okay, Boulder is a middle latitude station. It's not accurate anymore. So we use the little bar. And you can see there was a red bar means the Boulder station is affected by the aurora zone. And the blue bar means the time. Boulder station is after the aurora zone. So yeah, you can try to compare the time period, and typically during the red bar time period, and we have much more contribution from neutral wind. And if you try to look at the values, and I add a value on the top, and the ring current contribution to B to GMDs is roughly 150 to 200 nanosecond. And the contribution from a neutral wind can be up to 220. So that means neutral wind contribution effect on GMDs is comparable or even larger than ring current. We definitely need to include the effect from neutral wind when you study geomagnetic disturbance, GMDs. And finally, so we try to do a very simple step. At the open magnetic field region, we try to combine the neutral wind current with the magnetosphere current together before passing to the Poisson solver to get the potential, and to see if we have some current here due to neutral wind, do they have some feedbacks in the magnetosphere? And this is how it looks like. The specific time is 23 UT from May 2020. May 10th, the superstorm, and I'll be showing the two patterns from ring current. And the left one is without neutral wind feedback. The right one is with neutral wind feedbacks. You can see there are a little bit difference, as indicated by the arrow showing there. It's a little bit decreased due to the adding of neutral wind. And also we pick the full station from the simulation of SWMF, and we can get the DST index. So we have two lines, and the red line is the DST index from simulation with neutral wind contribution, and the blue one on top is without neutral wind, and you can see some difference. And typically, during the right part, which is the recover phase, as I mentioned, the recover phase, the neutral wind contribution is going to be relatively significant compared to magnetosphere source. And on the bottom figure, we try to do the difference, which is the black line between the top two lines, the two ranks. We have the brown color line, that is percentage difference. So seems like a little bit larger because they can be up to 30%. And this is basically the conclusion of this part. So neutral wind contribution to GMDs, they can be comparable, or even larger compared to rain current during recovery phase at middle latitude stations. And then the neutral wind driven current, they should have some feedback to the magnetosphere. Like they're gonna slightly change the rain current distribution and also change the DST index. And finally is question number 3. So now we wanna understand, so what are the typical scales of the IT symmetry? Because we know we have the high resolution super long observation on the left and high resolution all sky imager on the right. And we have very like from small to meso to large scale structures in the high latitude drivers. But when it comes to the satellite observation, this is from CHAP. Basically the neutral density observation, and we can only see some large scales because it's due to very cursor scan range. That means we do need more satellite to study the IT quantities. This is the reason why we need massive GPC mission. And for this part, we're going to study the multi-scale neutral and plasma perturbation with multi-satellite configurations. And so firstly, let's take a look at the neutral density. And here we're going to use the grid C and B satellite. They're going to give the neutral density variation, and we're going to have to validate the simulation result. And on the bottom, we use GITM again, but we just pre-design some satellite trajectories, and then put the trajectory information to the GITM simulation, and we can extract. Sounds like a satellite, but it's not a real satellite, so we call it virtual. And I want to briefly introduce the third one, which is the logarithmic. Because the two on the left, they're uniform, they are evenly distributed, but the third one is uneven distribution. The reason is we can study with this configuration, we can study small scales. Like you can see the first two satellites, they're separating in like 10 seconds. And we can study mesoscale, like you can choose 2 of the satellite pairs to get the mesoscale. And even we can study the inter-hemispheric symmetry, because at any time, the 2 satellites from very beginning and very last one, they're going to be like almost different hemisphere. So they can use to study inter-hemisphere as well. And so now is the actual result. So first we want to know does mesoscale neutral density matters? And we have one satellite, and the way we're gonna get the mesoscale is we're doing a time window average and then remove the large scale. So this is the residual, which we call mesoscale. And the top row is from GRACE observation, and bottom one is from GITM simulation. And they're showing the UT time and geo latitude planes. And the background, the lines, they're just A index and DST index. So, and you can see the mesoscale also depends highly on the geomagnetic activity. And you can see that in the polar region, the high latitude region, they have much narrower density structures. I mean, the latitudinal scale, you can see it's much smaller compared to the middle and low latitude. And also, if we try to compare this magnitude to the total density, the row density, so the percentage is roughly like 30%. That means mesoscale neutral density is like roughly 30% compared to the total density. That is not a small value, and definitely we should include the mesoscale neutral density. And then since we have more satellites, so how should we resolve the latitudinal propagation of this multi-satellite? And on the top right, we have the configuration. We have totally 6 satellites, evenly distributed in the meridional plane. And if we just pick one satellite and we get the observation, that is the top figure on the right. And then we can choose like 3 satellites in the triangle observation, the configuration. And then we have 3 satellites that is the middle figure. And if we're gonna use all the data, all 6 satellites, so we have the observation on the bottom. So you can see definitely with more satellite, we have more data, so we're gonna see more structures. But something important is with 3 or 6 satellites, you can see there is a neutron density, the TED propagation, very clear, but it's very hard to tell from the top figure because the top figure we only use 1 satellite. It's 90 minutes trajectory. It's quite crucial. And then we did the 2D interpolation and corresponding to the left figure. The reason is we want to do the 2D correlation to make sure which one is the uniform, the distribution. So the 2D correlation between 3 satellites and the 6 satellite is as high as 0.97. That means probably, at least for this event, 3 satellites in one meridional plane, this seems insufficient to resolve the most of the large-scale TEDs. And this is the conclusion from this study. But we want to understand, so why 3 is enough? So now we just pick the 2 satellite, which is like a 120-degree separation. That means 3 satellites in the uniform. And we just regard the 2 satellite elevation as 2 signal. And we plot on top, and you can see the gray and black line. They do show some difference. And then we're going to do a spectral analysis, and specifically we have the coherence analysis. And it looks like these 2 observations, they have nothing related. That means if 3 satellites uniformly organized in the meridional plane, which means 120-degree separation, they're going to observe exactly different stuff. So that's really why, at least for this event, and to resolve the large-scale TID structures. And finally, we want to try to separate the temporal and spatial variation because 1 satellite, they can't tell the difference between time and space variation. But if you have 2 or more than 2, you can do that. So this column going to show the time variation. Just think about if we have 2 satellites like moving one by one, and you first shift the time and then do the difference. They're going to give you the time variation at the same location, if not too much time difference, or at least the same local time. And then we have 3 pairs, and the top one, the 2 satellite separation is 13 seconds, and the middle one is like roughly 3 minutes, and bottom one is 10 minutes. So what we try to do here is we want to find the scale, time scale of the neutron density. And if we set the 10% as the neutron density threshold, and you can see for 3 minutes, which is a middle figure, they're going to be enough to tell you some difference between the time variation. And then we did the same thing, but for spatial. So spatial, again, we have 2 satellites. But if you directly do the difference, you're going to get the spatial variation between the 2 satellites. And if you have 2 satellites at different scales, you're going to have the spatial variation at different scales. And again, we have 3 panels, and we notice the spatial scale for neutron density is roughly 3.5 degree. So to simplify the scale, we found time scale is 3 minutes, and spatial scale is latitudinal is roughly 3.5 degree. And come to the conclusion. So we studied the mesoscale neutron density, their contribution, and they can be distributed in all the latitude, and the magnitude is roughly 30% compared to the rho, the total density. And 3 satellites evenly distributed in one meridional plane. They seem to efficiently to solve the large-scale TED structures. And finally, we find the typical scale of mesoscale neutron density. The time scale is roughly 3 minutes. That means after 3 minutes, where the satellite is separate longer than 3 minutes, you're gonna see something different. And the spatial scale is 3.5 degree in latitude. And so this is a little bit about the future work, because we study the neutron density, and people been asking about, so how about plasma? And this is plasma. The plasma is a little bit different because the plasma response time and the spatial scale is much, much smaller compared to neutral particle. We have to change the methodology. So that's the reason why we use the high resolution localized super long radar. And the super long radar resolution is 0.5 magnetic latitude and 1/5 local time. So it's very high resolution. And then we're gonna use this convection pattern to drive GATEM and to see some response. So we want to answer the question. So can GATEM plus super long plus virtual satellite resolve the mesoscale plasma? And here we go. So basically we have the first column is potential from the convection. And the top one is only have large scale. And bottom one is mesoscale. So you can also tell from the scales, right? It's very obvious. Top one is very large. And the bottom one is mesoscale because we are using the super long regional resolution. And then we're going to use the two corresponding potential to drive GATEM. And we take a look at TC. So you can see TC also very similar. And if you only have a large scale in the high-latitude forcing, you're going to see large scale in TC. If you have mesoscale in convection, high-latitude forcing, you're going to see mesoscale in TC as well. So that means typically this methodology, it works. And we can use this way to further study some study like this. So we put two very tiny satellites on the bottom. So this is the virtual satellite, and we're going to fly the satellite over the top one with large scale and over the bottom one with mesoscale. And we want to know if the satellite can tell the difference between the two different scale. So we have the right linear figure, and the two lines just mean the satellite flying different scales. And we pick the VI north at F region on the top, and middle one is a neutral wind north, very only neutral wind at F region, and bottom one is electron density. So you can see the two lines, they show some difference, right? Because the red line regional, they include the mesoscale, and they're gonna see something different. And we did quantify on the top the F region electron density. So we did the percentage difference. And the value showing that they can be up to 20%. That means mesoscale plasma or electron density at F region can be up to 20% at specific location. So if you're not using the mesoscale forcing to drive GCMs, you're probably gonna lose the 20% mesoscale in the electron density. So that's important. And coming to the final summary. So in this study, we raised the three questions and try to answer them. So first question is why in the half-two hemisphere they're asymmetric? And we did a comprehensive and looks like systematic study to investigate the main drivers, impacts, and relative contribution to the in-hemisphere symmetry in the IT system. And we also developed two different ways to quantify the symmetry. So to try to refresh the memory. So the step one, we found four different mechanisms: season, B field, and precipitation, and BY. And season dominates during normal conditions. And then in the second step, we picked the two forcing from the green box, and that is enhanced during storm. So we study a real event, and we noticed both the convection pattern and the convection pattern extension, they have the BY dependence. And finally, we studied the relative contribution between field current and precipitation, and also the asymmetric distribution and asymmetric magnitudes to the symmetry. So this is the first part on IT. And second part is we try to feedback the symmetric IT quantities. So first one on the left, we feedback the asymmetric ionosphere conductance to the magnetosphere. And the second one study on the right, we feedback the asymmetric neutral wind current back to the magnetosphere. And then look at some feedback in the magnetosphere in the whole geospace, which is significant. And thirdly, we try to answer, so what are typical scales of the IT quantity? And we use GDC virtual satellite mission with simulation from GATEM, and we get the typical scales of neutral density, at least we know during the event we are studying, the time scale is 3 minutes, and special scale, we have some values. And I think this is all I have today, and I'm happy to take any questions. Thank you.
Any questions?
Ask. Simple question. So, you talk about this case where the BZ was stable for several hours, and
Right.
then BY is like magnitude is
Positive.
same, yeah, positive to
Right.
negative, and what we see is most of the asymmetry is caused by distribution of the convection pattern, not the magnitude, right?
Right.
Yeah. So I think my question is that this is not a general conclusion. It is for this case, because some case might be more caused by magnitude. Yeah, less by
Right.
distribution. Yeah, I think it depends. Okay.
Yeah, I totally agree. Because another thing we achieved this event is this is near the equinox, and the two hemispheres
Yeah.
roughly have the similar, much similar background of the atmosphere. And yeah, and also we only focus on this small time period. It's like 10 hours. And during this time, everything is like not as significant as the other one. So we can just typically look at the BY effect.
Okay.
Yeah.
All right. Okay. Thanks.
Yeah, thanks.
Thanks for a great talk. I was wondering in the eclipse study,
Uh-huh.
because the eclipse, apparently it's very transient, very fast. Your simulation, how long? I mean, I'm not sure if you did a comparison study with or without. If you did, how long did they come back? Like, the trajectory or development come back together, or maybe they never come back. They just, diverge and develop in different paths.
So are you
IT system?
the whole IT system? I see. So yeah, that's a really good point. So far in the simulation I'm showing, it's only stopped at the ends of the solar eclipse. But if we did some check, like after the solar eclipse, they should be recovered. Yeah, but so far we only focus on but it's a really good point. I keep that in mind. Yeah, and right.
And also quickly, second question. At the very beginning, you mentioned the southern hemisphere response seems to lead the northern one. Did you resolve that, or did I miss that? At the very beginning, you showed.
There's also the solar eclipse.
No, this is at the beginning. You showed as one example of hemisphere difference, and you showed that the southern hemisphere response seems to lead the northern hemisphere response.
Oh, I see. It's from the introduction figure.
Oh, yeah, that's right. Yeah, that's one.
Yeah, the TC.
Yeah.
Hmm.
Resolve that. What's the cause of that?
The cause. So we can discuss about this because this is from previous study and from other people the study. There are some reasons. So I think I didn't add the time of the storm. There was some time delay between in the northern hemisphere. Not something late by the southern hemisphere, but just time delay. And we usually see the delay effect between the two hemispheres because the forcing input could be asymmetric and also due to the different seasons. Yeah, but I haven't checked this specific case because this is from
Which month? Which month is
Yeah.
I think it's 2018 paper. Yes,
I mean,
Which
the
month?
event,
the event.
which month?
Yeah, which month or season was it?
The season. Yeah, I didn't add the season of this event, but yeah, I should add it. But yeah, but I just want to use this figure to show there was some symmetry in TC. Yeah. Thanks.
Go ahead.
Yeah, your answer to question 2 is not particularly surprising, but I wonder if that answer means that approaches where one uses fixed driving for an IT model like GitHub be abandoned because those driving conditions are changing,
Right.
and there's probably a timescale issue there, but. This is another question I've asked often to various people.
I see. Yeah.
Yeah, if the magnetosphere and ionosphere are talking to each other and the linkage is pretty tight, it seems like if you cut that and just drive the ionosphere with one set of conditions, it might lead to misleading results.
Yeah, I agree. So yeah, we better think about the methodology. some, yes, the response between the magnetosphere and ionosphere should be like transient, like very quick response. Sometimes shouldn't be delayed, maybe due to the methodology. Thanks.
You are compared with that empirical drivers and realistic drivers. So what do you mean by empirical drivers and realistic? I think slide number 13.
13.
Yeah.
Okay, this one.
Yeah. So empirical, what I didn't get what mean to be a empirical drivers and realistic drivers. So driver means is the input conditions, solar wind drivers, or
That's a really good question. So this is the second part of our first study. So the first part of the first study, we directly use empirical model, use Weimar for potential, use actually A for precipitation. So that means empirical.
okay.
And empirical is typically, like you can tell from the top left, the CBCP, they're almost identical because empirical models, they typically developed, they just mapping the two hemispheres doing the average with data. And these are the empirical model. And the second one is a new methodology I introduced. It's one here. So it's based on real observation from unpaid field and current and based on AMA pattern, because AMA pattern is based on real observation. And that's the realistic driver.
And in that case, your hemispheric power has been observed to be shifted. I mean, in empirical driver, your northern hemisphere has more power, and in in the southern hemisphere,
I didn't get it. So what do you mean being shifted?
like for a last bottom panel where HP, where hemispheric power to the particle precipitation, you observe during that time your southern hemisphere is dominant, and in the next where realistic drivers, a northern hemisphere is dominant. Why there's such a difference?
So you mean if you try to compare the left empirical model, they reflect the relative contribution. And that's a really good point. And I mean, the left one is just empirical model. They add some, they could change the equation or something else, like based on season, different season, and then you got the two hemispheres, they have roughly the same variation, but the magnitude, you can't just reach the magnitude. But the right one is based on realistic data. It should be more like reliable, and it looks like the southern hemisphere has more not dominant, but much larger hemisphere power compared to the northern hemisphere. This is just our driver, and yeah, the question is why the southern hemisphere is more hemisphere power.
Is that the northern hemisphere more power? The northern.
Oh, the northern, my bad. Yeah, the
Yeah.
northern hemisphere, the orange color. Yeah, is yeah, they're not like related. So the right one, left one is just empirical model, and right one is based on real observation, and that's the case we see from the drivers.
I think we have one more question from online people. Could you unmute yourself?
Are you talking to me?
Yeah, I can hear you. Yes, please.
Okay. So my question is on the numerical side. Those are complex codes, and probably I understand that there is many time steps of integrations, and usually those codes do not, numerical codes very rarely preserve symmetry exactly. So of course, when the problem is like stable to non-symmetric perturbations, the code will, solutions will look more or less symmetric, but it's not warranted. So question is, did you test the contribution to non-symmetry from the code using some simple analytic setup to see how code itself reacts to non-symmetric perturbations? Like or in other words, how large is to observed non-symmetry is numerical contribution versus physical contribution?
Yeah, I really appreciate the question. So I'm assuming you're asking, did we test the symmetry caused by physics and numerical methods? The question is not yet so far, and because what we have been doing is for every case we typically doing at least two comparisons, and we're assuming the the two rands, they should have the roughly the similar contribution from numerical method, and then the symmetry is due to the difference between that one, and by doing the difference we can probably get most of the contribution from physics instead of the contribution from numerical. So that should be fine, but that's really good point. We definitely need to take a look at this kind of study due
And,
to numerical. Yeah,
and
thanks.
this is especially important in models that are governed by elliptic solvers, because elliptic solvers, I don't know what solver you have. Is it spectral or is it like a conjugate gradient on one of those Krylov methods? Because elliptic solvers, they have they may have lots of iteration inside. So it's like a multiplying number of times that by another dimension. And if there is a non-symmetry in elliptic solver, even small, it accumulates. You know what I'm talking about?
It's a direct solver.
Is it direct?
Oh. Yeah, they are. I think they are still using. We are still using a direct solver.
Speak louder.
It is not a positive definite matrix. Neither it is a symmetric matrix. So there isn't efficient technique to invert the matrix.
Yeah, but is it iterative or is it spectral, or how do you do this? There are different methods.
Yeah. I mean, this is a direct solver, so I think it's kind of LU decomposition type.
Yeah.
Mhm.
Conjugate gradient is considered, for instance, Krylov solvers are considered being direct methods because in a limit of infinite resolution, they give you exact, or in a limit of infinite iterations, they give you exact answer. But still, in practical applications, they have errors, and they might have symmetry errors. Anyway, so that the answer is that you will look to it, right?
Mhm.
Yeah.
Thank you. Yeah, I really appreciate it.
Okay. Think if there's no further question for you.
There was in
One, another one?
someone was asking.
Is there, where's
On Slack, I think in text.
Oh,
Arena as
in
well.
chat?
In chat.
Okay, so slide 9. How do you quantify the asymmetric particle precipitation flux? Are they measured? Are they measurements? Do you know slide 9? That are there measurements that validate the asymmetric input of particle flux into GITM?
Okay, so the first question, how do we quantify the symmetry of precipitation? So we have two different ways. The precipitation pattern is like 2D height integrated values, like a 2D array. And we just do the 2D correlation to get the symmetry. And also for precipitation, for each hemisphere, we can get the integrated value, which is a single value, single number for each specific time. And this is regarded as the total energy input. So we can do that one with the first symmetry index as well. And I think the second part of the question is, are there any measurement satellites that validate the symmetry input of precipitation? They definitely have a lot of measurements for precipitation. So like I was showing the imager, you can take a photo of the precipitation, like a gold satellite, not gold satellite, I think it's imager, and they can do that. And also DMSP satellite, they can give you the tracks of the precipitation, and can also be used for validate the observation of precipitation. And what we're using is directly get the 2D array of the driver and then do the simulation. And I think that is something related to the driver parts. And hopefully that's the answer to the question.
Cool. If there's, okay, any other questions? If no, let's thank Hongyu again, and then